So let's prove Azimuth inequality. Again, we want to consider the exponential function. Take the exponential function on this random variable, and apply Markov inequality there. That's what we want to do. For that, let's collect some claim. So when we have a random variable x, which takes the value in real numbers and which has the expected number 0, and the value of this, the absolute value of this is never more than some constant c, then we can actually bound the expectation of e to the x by e to the c plus e to the negative c over 2, and which can be again bounded by c squared over 2. The last inequality is not so difficult because you just take the Taylor's expansion. Then this is 1 plus c plus 2 over c squared and 6 over c cubed and so on. This is same but alternating sign. And you add them together, then this part cancels out the remaining one, and you divide by 2. Then you compare that with the Taylor expansion of this. Then the last inequality is not too difficult, but we also have to prove the first inequality. For first inequality also it's not difficult. We know that the function f e to the x is a convex function. Say on this. So you have negative c and c, and then there you have a convex function. Then you take the two ends and then take the weighted average. Then that's always above this value. That's one of the property of convex function. Hence what we have is, if you take this e to the x, then that's at most this weighted average. And when we take the weighted average, you take this value, this ratio, and then you multiply this, and then you average out. So the length is 2c, and this length is c minus x times e to the c, and e to the negative c, c plus x, e to the negative c, which is 2 to the 2 under e to the c plus e to the negative c, and this. And obviously c has to be positive number. Now you take the expectation. This inequality holds, so if you take the expectation on both sides, the inequality must still hold. Then, this x is between negative c and c, so, no, not that. So, but we know that this expectation of x is 0, so this part becomes 0. So you have this inequality, and that obviously stays by this. So we get the claim. So now we prove the Azimuth inequality using this claim. First, we replace xi with xi minus x0 if necessary, to assume x0 is 0. So by shifting everything, we can assume that the initial value x0 is 0. And let yi be the difference between xi and xi minus 1. Then the condition implies that yi has size at most ci. And expectation of yi assuming x1 to x minus 1 is 0. So because xi are martingale, so expected change is 0. And now what we want to do is we want to analyze this. So this is random variable. So assuming this, now you consider that, and that's our random variable in this claim, because its expectation is 0 and it's never deviate more than ci. So this is at most e to the t square ci square over 2. So the value t will be determined later, but we have this inequality. Moreover, what's the expectation of e to the x txi? Which is same with this. And what's this expectation in here? In here is we consider all the possible value of x1, x2, x3 and so on. So this is actually can be taken into two expectations. One is over yi, and one is over x1 to xi minus 1. And you can take the first one here. You can take the y part out. Then you can rewrite the entire thing in this way. And what's this? Then that's by above you have the inequality. To be more precise, we can write it this way. Then that's at most this much. So you can conclude this. So you repeat this to take out more, and then the same expression with I minus 2, and we do that, then expectation of e to the txm is at most expectation of summation, t square summation of ci square over 2. You take this term and then you multiply, then the exponential parts adds up. The exponent adds up. So you have this. Then if you use the Markov inequality, so we use the Markov here with t being lambda times summation of ci square to the negative 1. Then what's the probability that e to the txm is bigger than e to the t lambda? So we want to estimate the probability that xn is bigger than lambda, which is same as this probability. And by Markov inequality, this is at most e to the t lambda or under expectation of t to the e to the t xn. What was this? We have exponential function of this minus t lambda. But what was lambda? Lambda, you multiply t is that, so this is t times lambda is, you get this. And then you have t square, you put it here, then you get this. So you have that it's at most this number. So which is exactly what we wanted to prove, the Azimuth inequality. So we have this. So we have this Azimuth inequality, and we want to apply this to, some problems that we want to show. For that, we need to set up a right martingale. But usually this martingale is exposure martingale that we have learned. And we also have to check whether this is actually satisfying this condition. Sometimes this is called Lipschitz condition. Depending on this value, C Lipschitz or something. Anyway, so, okay. We will define what Lipschitz mean in a more rigorous way, but in order to, when we consider this as an exposure martingale, so for example, here, if you consider the coin flipping example, and each time you flip a coin, then in your process, the number of heads changes by at most 1. But your martingale is not that. Your martingale is this expected number of that conditioning on the previous one. So we need to show that in each time, the how it changes from yi plus 1, we need to check that that never changes with more than certain value. So that's, slightly different thing. That's actually a different thing. So in the process, every time you flip a coin, then the number of coin might change at most 1. It could stay or it could increase by 1. But at the beginning, this value was half n. But when you go to y1, then it becomes half times n plus 1 or half times n minus 1, depending on its head or tail. And y2 as well, y3 as well. So you can actually check that in this simple example, every time the value changes by either half, at most half. So it goes up half or goes down half. For more general, martingale, which is exposure martingale, for example, this edge exposure martingale, if you change the one edge on graph, then chromatic number can change by at most 1. That is true, but if you take this exposure martingale, edge exposure martingale, and if you change one value, if you determine one value from here to here, is it obvious that the changes are bounded by certain number? It seems that in here, it never changed with more than half, right? 0.5 to 3 or 1 to 2. It can change up to half. But it's not sure whether, we can prove that in any case, once you add an edge, the chromatic number, the expected chromatic number, how much it changed. So, our intuition tells that it must be at most 1, but we have to actually check it properly. So it is not that obvious that it holds. So I mean, in the next time we will show that when we have an exposure martingale with a correct function, so this is exposure martingale with certain function f, then I mean, then if the original one satisfy that this f satisfy certain good condition, then it is always satisfy certain condition that we require. That's what we will prove next time.